So, good morning. Welcome to Krishna's classroom. We now take the next step in defining the Lebesgue integral. Recall that in the last lecture, we looked at the Lebesgue integral of simple functions on sets of finite measure. So, naturally, as I listed out in the first part of this lectures on Lebesgue integral, you stage by stage you define it. Okay. So, for simple functions, we have now introduced the Lebesgue integral. Next stage is we will make use of these definitions or make use of simple functions to approximate approximate bounded measurable functions on sets of finite measure. So that gives a mode of reaching out to define the integral, the Lebesgue integral of such functions. So let us assume the following, fix the notation. So let E be a subset of the real line. Then measure of E is assumed to be finite, and F is the generic notation that we use. F from E to R the bounded and measurable. Wherever we deviate from these conditions, we will make a mention of it. Okay, so this is the basic assumptions that we make. Now, as we did for the Riemann integral, if you recall, we used step functions. Okay, and we approximated the function with step functions from below and from above, because we were working on bounded intervals and the functions are assumed to be bounded. So we were approximating them that from above and below by what are called step functions, which we have considered in detail. Now we do a similar exercise here, and what we do is the following. We are looking at bounded measurable functions on sets of finite measure and try to approximate such functions by what are called simple functions from above as well as from below. So what happened in the case of Riemann integral? We defined two sums, namely lower sum and an upper sum, and if at all the function is integrable, then we found that this has to be squeezed between the integral of the upper sum is squeezed between the lower sum and the upper sum. This is what we have found. And then of course we took the supremum of all lower sums and infimum of all upper sums over all partitions of the interval into subintervals. Okay, and we said that f is Riemann integrable provided the supremum and the infimum that we have defined turn out to be the same. Okay. I mean, that was the strategy. We do a similar strategy. So we define what is called lower Lebesgue integral. That's what we define. Okay. Lower integral of f where these conditions are satisfied is defined by supremum of integral of phi over E. This is the Lebesgue integral. Phi simple and phi is less than or equal. This is the lower Lebesgue. Now similarly, we define what is called, you see, first of all you see that there exists simple functions below the function f, that is this condition satisfied. So there exists such functions. Now over such functions, for each of these functions you can compute this integral E over phi because we have already defined it. So these are some numbers. So it's a number collection of numbers. And you see that these numbers are bounded above. That I shall make a remark about it soon. Because all the upper sums, okay, or upper integral that we define are bounds for all the lower integrals. Therefore, this is bounded above. Therefore, the supremum exists. Okay, so that is what you call the lower Lebesgue integral. Second part is this. Upper so we can, if you want, you can designate this by L LF. I will denote the upper integral by the upper Lebesgue integral of f is defined by UFE, which is defined as infimum of integral psi over E, psi a simple and all the psi's are bounded below by E. So this is what we have. Okay. Now our statement is that both lower and upper Lebesgue integrals exist. How do we look at that? So note that f is bounded there exists simple functions phi such that and psi such that f. Then we have seen that both integral phi and integral psi exist, and therefore by the boundedness of f, these are bounded functions and their integrals are finite. So integral over E phi and integral over E psi finite, and integral over and LFE, see integral of integral over E of phi is less than or equal to integral over E psi, where phi and psi are as we have defined here. That means you have phi less than or equal to f, psi less than or equal. So this is what you have. Both phi and psi are simple functions such that this. Therefore, this is satisfied. Okay. Okay. So L F E is bounded above and UFE is bounded below phi bounded above U psi B is bounded B for every these are simple functions. Phi and psi are simple functions, and this condition is satisfied. Okay, which implies LFE and U therefore these are well defined. Okay. Now with this, what we observe is that the lower integral is at most as large as an upper integral. So also the upper integral is as large as the lower integral. Further, L this is true. Now I think we are in a position to define when is F integral. So for all f of this class, the upper and lower integral exists. Okay. So now we shall define as we did in the case of Riemann integration, what we mean by integrability. Okay. So if these two are equal, in the Riemann integral case, you recall the upper integral and the lower integral. When they are equal, you said f is Riemann integral. Likewise, here we say that f is Lebesgue integral if both LFE and UFE are. Okay, so that's the criteria. We can now write down the definition. A bounded function f on a domain E of finite measure is said to be Lebesgue integrable over E, provided its lower integral L F E and the upper integral exists you see, you don't have to assume that the function f is measurable to get the existence of lower integral and the upper integral. Okay. Sorry. Need that assumption. Yes. F is measurable. Yes. That's right. F is measurable. Okay. We need the assumption that F is measurable. Yeah. I'm sorry about it. Okay. Now what we have is that both these upper integral and the lower integral are equal. So a bounded function f on a domain E of finite measure said to be Lebesgue integral for E provided lower integral and upper integral exists and are. The common value of and is called the Lebesgue integral of it's called the Lebesgue integral of f and is designated by integral over E f. So that's the definition of the Lebesgue integrability of. So if f is Lebesgue integrable, then you have both the upper integral and the lower integral equal. Okay. Or if the upper and lower integrals are equal, then you say f is equal. So we have defined what Lebesgue integral is. And you can see that it exactly runs along the scheme that we used in the case of Riemann integration. Okay, right? There is a lot of similarity. Now, where does it differ? I will see this. Okay. Now, what we prove is this, that if f is a bounded function defined on a closed bounded interval AB and f is Riemann integrable over AB, then f is integrable over AB. So this is the checking of our path, whether we are on the right track or not. Okay, so what we do is, are we getting a generalization of the Riemann integrability? Okay, so that's the question that we are asking at this stage. So we prove this. All Riemann integrable functions over bounded intervals are Lebesgue integrable. Okay, so this is what we want to do. We shall first verify that we are along this right track to generalize Riemann integral. We prove this by, we establish this by verifying that all Riemann integral functions bounded functions all Riemann integral functions, or I'll put it this way, all bounded functions bounded intervals, bounded closed bounded intervals contained in R Riemann integral. Lebesgue integral. That is F Riemann integrable implies F Lebesgue integral, and the Riemann integral of F over the interval AB this is the Lebesgue integral. So this is what we want to do, so that we are on the right track. So let us state the theorem. Let f be a bounded real valued function on a closed bounded interval if f is Riemann integrable, then f is Lebesgue integrable. F is Lebesgue integrable. And the two integrals coincide. That means all Riemann integrable functions are Lebesgue integrable, and the two integrals coincide. Now, this is quite easy to prove because let us take, we assume is Riemann integral. We have earlier designated this as script R of AB as Riemann integral functions. Let then what you have is the following. Okay. Supremum of, that is, this is what you have. The lower integral of I will put it this way. Get the right option. or LFI, which is equal to supremum of the Riemann integral of over I of phi, where phi is a step function, subordinate to some partition, and phi so that supremum is taken over all step functions which are bounded above by f. This is equal to infimum of psi is a step function such that and this is essentially our designation FUFI. Okay. So LFI is equal to UFI. That's what you have. They are equal because F is Riemann integral. Okay. Now let us make some observations. See, what we are doing is this. When we define Lebesgue integration, what we are doing is we are taking the supremum is taken over all simple functions, not step functions. All step functions are simple functions. So we are making you to use that. Okay. So now you observe that supremum or LFI right here, LR. LRFY, this is to do with the Riemann integration. That's why I'm putting R here. This is certainly less than or equal to our definition of LFI. LFI. What is LFI? LFI is supremum of the Riemann integral of phi. Riemann integral of phi is the same as Lebesgue integral of phi. Therefore, integral over phi a simple function such that phi is less than or equal to that is your LFI. And this in general is less than or equal to what? UFI. This is certainly less than or equal to infimum integral over phi of phi a simple function such that psi is greater than or equal to, which we have designated by UF because it is on the I, and that is going to be less than or equal to okay, let us look at these two things. LRFI is less than or equal to LFI. What we have the following. Okay, you know that every simple function, see, these are all simple functions, and step functions are a subcollection of the simple functions on the interval. Okay, so that's what we are. Therefore, in the first place, we also observe that if you are using see, these simple functions are all integrable. That's what we have shown. And whenever phi is a step function, the integral of phi, that is the Riemann integral of phi, is the same as the integral of phi. Therefore, you see that this inequality is perfectly well. Now, what happens here? This is a smaller collection, and we are taking the supremum over a smaller collection when we do this Riemann integral. And when we do this over a larger collection, now you see that the supremum is likely to be larger. Okay, that's why you get this inequality. That is, note that for the simple reason that simple functions this is the reason. Similarly, you have UR once again for the same reason, that is, simple functions on I are larger, from a larger collection than the step functions, and every step function on I is a simple function. So this condition is satisfied. So here we are taking the supremum, therefore the inequality goes like this. Here we are taking the infimum, therefore the inequality goes in this direction. So what do you get? You get LR you compare this with what we did in the case of the Riemann integration. Okay, this is what. Now what we assume, since f is Riemann integrable, LR which implies from this inequality L F I or what you have, f is integral. That is, f is integral. And the two integrals coincide. So we are on the right track. So all Riemann integrable functions on bounded intervals are Lebesgue integrable. And the Riemann Lebesgue integral. So that completes the proof. So all Riemann integrable functions on bounded intervals are Lebesgue integral. And the integrals coincide. That's it. So that's the conclusion. Okay. Now, remark there exists bounded functions on which are not Riemann integrable but are Lebesgue integral. So you see, it shows that there is some improvement on this. For example, we take f characteristic function of q. Now this we have analyzed earlier. This is the function which takes the value 1 at all rational points on the interval 0, 1, elsewhere 0. Now you see that the Riemann integral of f exists because what is the reason? The lower is strictly less than this is equal to 0, which is equal to 1. On the other hand, the integral f on 0, 1 is equal to 1 into measure of, because it's a simple function, measure of q. In fact, this is also true. Complement. Now you see that measure of this is equal to 0, measure of this is equal to 1. Therefore, this is equal to 0. Therefore, this is integral. You see that both f is a bounded function taking only two values, namely 0 and 1. Okay. Therefore, this is what you have. So, this is an example of a function which is bounded on a compact interval 0, 1, which is not Riemann integrable as we have seen earlier. This is the Dirichlet function. Okay. That is the Dirichlet function. Is integrable but not Riemann integral. So that is what we end up with. Now what? So the next thing is we want to work on all bounded measurable functions on a measurable set E of finite measure. So we take the general theorem, the central theorem, that we prove that all bounded measurable functions on a set of finite measure is integral. the main theorem. Says that all bounded measurable are integral. Whereas you see that the example that we have looked at, that is the Dirichlet function, is a function of this class, but it's not Riemann integral. So the class of Riemann integrable functions is smaller than the class of Lebesgue integral functions, and smaller in the sense of setting Gaussian. Okay. So we will work it out. So we state the theorem. This is the central theorem. Okay. Let F be bounded measurable function each one of these conditions is very important. On a set E of finite measure, or simply integrable over integrable over. So every time we avoid saying Lebesgue integrable and simply say integrable. Whenever we say integrable means Lebesgue. Okay. Let us now prove this theorem. To recall, for these class of functions, okay, for these class of functions, we had what is called the simple approximation theorem, guaranteeing that it can be approximated from below by simple functions and approximated from above by simple functions as closely as you want. Okay, so this is the result that we are going to use. Let n be a natural. by the simple approximations theorem. There exists simple functions phi n and such that further phi n and psi n may be chosen such that 0 is less than or equal to phi n So by choosing n large, you can make these approximations as closely as you want with f. That's the point. Now that's a simple approximation theorem that we have proved and discussed earlier elaborately. So now by monotonicity and linearity, of integrals on simple functions we have this 0 is less than or equal to integral over e which is equal to integral over e which is less than or equal to 1 by n into measure of e is finite. Okay. See, the simple approximation theorem assures that there exists such functions phi n and psi n. So you are approximating from above by psi n's and from below by phi n's. And in fact, f is squeezed between psi n and phi n. So all this measurability of f etc. have been made use of in proving the existence of such functions. So we don't have to really work on that. So what do we do? Right. Now 0 is less than or equal to u uf, which is equal to and minus yes, Fe, which is equal to infimum of integral over minus this is what you get. Okay, and this is now, see, this is the infimum of all this. So integral of phi n is something bigger than this. Therefore, integral of psi n minus integral of over E of phi n, and this is equal to integral of over E of, which we have evaluated, and this is less than or equal to 1 by n measure of P. So this is the estimate that you have, and of the difference between, so 0 lies between UFE minus LFE. So for any n, this is true. Okay, this is true for every natural number which implies since measure of E is finite, follows that integral that is f is Lebesgue. So that completes the proof of this. Okay. Now we make a remark. The remark is this, that the converse of the preceding theorem in the following. A bounded I'm not assuming it's measurable function on a set of finite measure is integrable if and only so you recall this. If f is if you have a bounded function which is measurable, then it is Lebesgue integrable. Conversely, suppose the function is Lebesgue integrable. We are not assuming it is f is measurable, then we are able to infer that f is also a measurable. Okay. So measurability is, so this is the if and only if condition. So this is the form in which we would like to prove this theorem, but we postpone the proof later. So we have proved in the backward direction. The forward direction we prove or we postpone the proof. So that's what we right. Now we show that see, if measurability is not assumed, then the theorem may fail. Okay. We shall observe that. Assumption. For in the absence of it, integrability is not issue. Okay, let us look at the example. We look at the following example. Let E be positive measure. That is, measure of E is positive and plus finite Now we will look at this function. Then there exists a which is not measurable. That means all non-zero sets of non-zero measure has some subset which is not measurable. That is, we have E1, so E1 contained in E. E1 is not measurable. Now take this, consider characteristic function of equilibrium. F is bounded. And defined on E, but not measurable. Because E1 is not measurable. And does not exist. Because it has to be the measure of E1. Measure of E1 is not defined. And that's a nice place to stop. In our next lecture, we will be exploring some of the properties of or the Lebesgue integration. Okay, so that will be our next task. It's a routine sort of thing that do. We did that for simple functions last time. Similar properties we explore for what are called bounded measurable functions on a set of finite functions. Thank you very much.